Hello and welcome to your lesson on solutions and solubility. We are going to talk all about solutions, how they form by dissolving stuff to make a solution, and also talking about different types of solutions, and then also solubility of things that we put in to make solutions. So I keep on saying the word solutions. We're talking about solutions today. Just a reminder that when I say solutions, that is another word for a homogeneous mixture. And normally I'm talking about one that is liquid. All right, so objectives. I can investigate the solubility of different materials. I can investigate and identify facts that affect solubility and the rate of dissolving, and I can relate the properties of mixtures and solutions to the particle model of matter. So that is what we are tackling today. So before we get into it, let's talk about what is actually happening in a solution. So what are the particles doing when we have a solution? And the answer is, when we have a solution and we can no longer see the solute. So you put sugar in water, you stir it around, and you can no longer see the sugar. The reason why is because the sugar has been broken into teeny tiny molecular sized particles that are evenly distributed throughout the solution. So evenly distributed means that they're all over, right? Evenly placed. So there's no part of the sugar water that has more sugar than the other part. It's all evenly distributed throughout that solution, and you can no longer see it because those sugar particles are so tiny that they no longer scatter the light. You can no longer view them. Don't know what else to say about that. I mean, think about the fact that when you put sugar in water and then you drink the drink, you don't have like one gulp where you're like, oh, that's so sugary, where you get a bunch of sugar in one gulp, and then another gulp you're like, oh, I don't taste sugar at all. It all tastes the same because of the fact that it's evenly distributed. It's all the way throughout. And everybody drinks sugar water, right? This is a thing. You just mix up some sugar and some water and have that? No? Okay. All right. I mean, in all honesty, me either. I'm not really a huge sugar guy, but yeah, if you did, that's what you get. Anyways, solutes and solvents. This is terminology incredibly important for a solution of what is what. The solute is the thing that gets dissolved. It's normally what you have less of, while the solvent is what is normally doing the dissolving. Now, how do you remember that? Because you have two S words that are so similar between the two. So how can you tell which is which? Well, solute is the smaller word. This has only 6 letters, while solvent is the larger word with a whopping 7 letters. So you can remember that solvent, the larger word, is what you have more of. It is what is doing the dissolving, while the solute is what you have less of, and it is getting dissolved. So for example, in our sugar water example, the solute would be sugar, and then the solvent would be the water that is dissolving the sugar. Okay, so that is solute and solvent, two very important terms. So what is happening when a solute dissolves? We've talked about this a little bit, but what is actually happening is that the solvent particles are breaking apart the solute particles from each other. So the solvent particles are more attracted to the solute particles than the solute particles are attracted to each other. So as a result of that, the solvent particles end up surrounding the solute particles, and then they spread throughout the solution. Let's use an analogy to make sense of this. Let's say that you're at a dance, okay? And you've got like, general high school dance. You've got a group of guys on one end of the gym or wherever you're dancing, and then a group of girls on the other end of the gym. So in order for us to actually get guys dancing with girls or whatever, what's going to have to happen is that they are going to have to mix around. So basically a guy is going to have to go grab a girl and separate, and then they're going to dance together, that sort of thing. And that would be the act of dissolving, right? In the meantime, these girls are just kind of sticking together, right? They're just kind of feeling safe together, all together. I don't know what else to say. So they need to be separated by the solvent's action. So what I end up having is all of this sugar at the bottom of the water, right? All this sugar that then the water needs to separate the sugar particles from other sugar particles, and then it goes and evenly distributes throughout that solution. Hopefully that made sense. This is a really nice animation that actually shows this, and I think it even has some words and stuff. So let's see if we can make this function. No. Is it not going to do its thing for us? Oh, what a shame. What a shame. Here, let's do this instead. We're cloning it and then we'll watch it.
Add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale.
Let's do it.
Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
Okay. Don't worry too much about the positives and the negatives. What we care about is the fact that the water is carrying away the particles. Look at how the water was surrounding particles and then taking it away from the rest of the solute. So that's what's happening, is the solvent is actually tearing particles apart from the solute in order to evenly distribute it. It's actually quite a violent process of what's occurring. Okay, so when we relate this to the particle theory of matter, remember the following. Number one, particles attract each other, and particles are always moving around. So in the example, a group of water particles can attract a sugar particle more strongly than the other sugar particles around it are attracted to that particle. So as a result, it gets separated. It's kind of like if you're with a group of friends, and then you see friends that you like more, and you're like, I'm going to go with the friends I like more. Just kind of horrible. You should stick with your original friends or get them all together. But you know what I'm saying. You separate in order to go with what you're attracted to more, essentially. All right. So the term soluble, what does it mean when I say something is soluble? What that means is it will dissolve in the solvent I'm talking about. So typically we're talking about water. So if I say it's soluble in water, that means it will dissolve in water. Some things are soluble in, let's say, instead oil, okay, or a non-polar solvent instead of water, or maybe they're soluble in ethanol, alcohol, or whatever. So when I say that something is soluble, I'm saying that it will dissolve in the solvent I'm talking about. And again, remember that the solvent is the thing doing the dissolving. In contrast, if I say insoluble, in means not as a prefix. So if I say insoluble, I'm saying it doesn't dissolve. Okay. Did you know that water is called the universal solvent? Now, it isn't actually a universal solvent, because if it was, it would dissolve absolutely everything, and baths would be horrifying because you would dissolve in the bath. You don't want that, but it does dissolve a lot of things. And that's true for water because of its very small size, and it has a polar thing going on, has a positive and a negative end, and other reasons that don't matter for Science 8, but just know that water is a very good solvent. So, is sugar soluble in water? Well, hopefully at this point we've already answered that. The answer is yes. Is oil soluble in water? You've maybe seen this before. We're going to do some kind of a solubility experiment coming up here where you'll test a few things. But the answer for that is no, it would be insoluble in water. Oil does not dissolve in water. Same thing with, for example, gasoline. Gasoline is insoluble in water. It does not dissolve. All right, so what actually affects the rate of dissolving? In other words, how fast something dissolves. So you put some sugar in water and you want it to dissolve fast. How do you make that happen? Another way of thinking about this is, let's say you're making iced tea. You want to make some delicious iced tea and you want to dissolve it as quickly as possible so you can enjoy your delicious sweet beverage. So some things that will affect how fast something dissolves, right? Rate is a fancy word for how fast. Agitation is 1. So if you stir it or shake it, that's going to speed up the process. And the reason why is because then you're getting the particles moving more. More movement of particles, that means it's more able to separate solute from other solute particles and surround it as a solvent. Temperature, actually for the same reason. The higher the temperature, the more ability it has to dissolve and the faster it will dissolve, because temperature is a measure of the average kinetic energy of particles. So temperature is how fast the particles are moving. If particles are moving faster, they're more able to break up solute than if they're moving slower. Think about it almost like wind or something, right? The higher the wind, the faster the air is moving, the more it's able to wreck stuff and kind of tear things apart. The same way, the faster the particles in the solvent are moving, the higher the temperature, the more it's able to tear apart the solute from each other into that molecule-shaped size so it evenly distributes. Another thing is the size of solute. In other words, if you have a powder versus a cube, right? The powder is going to dissolve faster. Think about a sugar cube compared to, let's say, granular sugar. Okay, if you have sugar as grains, it will dissolve faster for the same amount than a sugar cube because you have more surface area. In other words, it's already in tiny little bits, so it's easier for the water to break apart the solute particles because it can get to more solute particles from the very beginning. All right, so here's some pictures to go along with that. Agitation, mixing it. Surface area, right? So cube compared to powder, this will dissolve much faster than this. Temperature, higher the temperature, the faster the dissolving. One that we didn't mention because it's not really a factor for solids dissolving in a liquid solvent is pressure, but that is a factor for gases dissolving in a solvent. So for example, carbon dioxide and pop dissolving in a solvent, the colder the solution is, this is pressure. The higher the pressure, the more it can actually dissolve. But we will not really consider that or worry about that right now. All right, solubility. Getting to the end of the terms here. Solubility is the mass of solute that can dissolve in a given amount of solvent to form a saturated solution at a given temperature. So it's how much could possibly dissolve of solute for a certain amount of solvent. So for example, if I had 100 grams or mils of water, it's how much could actually dissolve in that 100 grams of water at, let's say, 20 degrees Celsius. So if I had, let's say, 10 grams of salt dissolving in 100 grams of water, and that's as much as I can dissolve in that water, then that would be the solubility of salt in the water. Okay, we're going to deal with this more later, so I'm just briefly covering it now, but we're going to actually get into solubility graphs here next week, and then we'll discuss it in more detail. All right, some other terms, and then we're done. Saturated solution. Saturated solutions means that as much solute as could possibly dissolve is already dissolved, and if I added any more solute, it would not dissolve, but it would end up on the bottom undissolved. Okay, so saturated means no more could dissolve. Unsaturated means that more could. I could add more solute and it would dissolve. So if I added more sugar, then it would be able to dissolve. That's an unsaturated solution. And then supersaturated, this is a weird one, and we're going to have videos for this so you can see. Supersaturated means that more is actually dissolved than should be able to stay in the solution. How we make a supersaturated solution is we actually heat up the solution to dissolve more, and then we carefully cool it down. And without there being a spot for things to crystallize on as solubility goes down, it stays in solution. And so as a result, what happens is that we end up actually getting a supersaturated solution. And then all we need to do is create a place for crystals to start forming, and then all of a sudden, all the solute comes out of the solution. It's really crazy to see, quite bizarre. So, videos. What's the difference between a saturated and an unsaturated solution? So 2 different terms. Saturated, no more can dissolve. Unsaturated, more solute could dissolve if it was added. Okay, so we could get more in there. So that is really it. So that's our brief discussion on dissolving and solubility and stuff, solute, solvent. We're going to get more into detail and continue our discussion of this in future lessons. All right, have a good rest of your day.